Hello, it's really nice to meet you. It's great to be here. Yeah, yes, some people say Oxwash. Yeah, I am a PhD student currently in the engineering department, so I do a lot of machine learning stuff. But my background and my undergraduate degree was in computer science, so we're going to talk about some computer sciencey stuff today. Yeah, um, I hope you're all doing great. I hope you can hear me okay. I hope I won't bore you with some computer science concepts. I hope it'll equally be as interesting as maths is to you. Um,
Thanks,
yeah, and
Ola.
hopefully, yeah, no problem.
Yes, no, sorry, I forgot to unmute myself.
Oh, classic.
Hello and welcome back to the Oxford Online Maths Club. I'm James. I'm an idiot, and this is Ola.
Yeah, I've
Right,
introduced myself already.
if you want to join in with chat, which is currently mostly people telling me they can't hear me, thank you, chat. You can join in at slido.com/OOMC, which is also where you can see the how was your day to day poll. Uh, I thought I was having a 5-star day until I managed to unmute the wrong button in in OBS. How's your day going, Ola?
Yeah, it's been really good. Very relaxed today because I was at home for most of it, but it was lovely and sunny, so really enjoyed it.
Yes, the weather is amazing in Oxford right now. People in chat are so far having a 3-star day. Oh dear, which
Oh,
is in the middle. Uh, so that's not what I want to see. We'll give them a moment, see if they're having a 3-star day. Yeah, good. Right.
oh, better.
Now I'm.
Your answer, I think, biased the audience.
Yes. Um, good. I can't. I'm trying to remember what I said, but while I was on mute, nothing important. Look at the things on the screen, everyone. It's problem solving matters, which is a course for people at various venues in the UK, of which Oxford is one of them. It's run by MEI, and it's a course teaching people about problem solving skills for maths. It's probably the most useful for people who are getting ready to do a maths admissions test, like, for example, the maths admissions test, which is what we use for Oxford's undergraduate courses. There are others, but ours has got maybe the most down the middle, straightforward name for it. Uh, right, yes. Aaron in chat would like to know when they'll get a response from Promise Europe, and I'm afraid I don't know. That's for the Promise Europe team, I'm afraid. Right, good. Comment about my dress sense. Right, good. Not that sort of doctor. Also have. We don't always do this, but I have another poll. We have another poll question, um, which is people in chat know about promise. Excellent stuff. Uh, I because it's the last episode of the term and I have to write a report. Don't worry, we're not going anywhere.
Oh,
We're coming back, but we're going to take 2 weeks off for the Easter holidays, during which I have to write a report on how things are going. I would like to ask one question, if that's all right, for people in chat. It's about university. We haven't really talked about university at all. I'm interested in whether people watching Maths Club Live are people who are about to apply to university, people who already applied to university and are getting ready to be at university quite soon, or just like neither of those, in either direction. I don't know. Sorry, I'm talking way too much. I promise I will let you
no,
do some
not at
computer
all.
science in a second. It's so far as mostly, I think.
It's really interesting to know who the people in the audience are. I'm also very
This
curious,
is
so
also
this is
maybe
great.
helpful for as we
Exactly, exactly.
as we think about showing people a bit of computer science and a bit of other stuff. So we'll let that run for a second. People in chat. Good. Okay. Yep. And
So quite a few people going to university next year. Very exciting. Best of luck with all the applications.
yeah, which is nice. I guess in England, I would say that might be year 12 or something. If we're thinking about But it's not just people in England. Or I could do a poll question: is this just people in England? Let's not do the poll question: is this just people in England? Cool. Right. That's got about the same number of votes as the How Was Your Day poll, so I'm going to call it there. Thank you very much for doing my survey. Feedback. Right. Okay. I've done a microphone gaff. I've done a I've done a poll. It's time for me to stop talking. And I did the owner, I think. Thank you so much for coming on the show.
Of course, thank you for having me.
I think so. You wanted to start with these 3 pictures that we found on the web, right?
Yes, exactly. Yeah, so these should give you a little hint to what we're going to cover today, what will be our topic that we're going to dissect. So I would like to ask you, if at all possible, to type in what your best guess is for what we might be discussing today based on these little photos and pictures.
I like the cat one best.
I believe I can see one answer that says Fibonacci on the screen.
Yeah, let's give them a second. See if people want to guess other things. Yeah, somebody in chat.
Fibonacci spirals. Spot
Fibonacci
on.
spirals.
Fibonacci sequences.
Fractal sequences in general. And a few people are saying
Yeah.
the golden ratio.
Oh, perfect.
Aaron's
Yes.
been looking at these already for 3D design reasons. Yeah.
Oh, very nice. Okay, great. Fantastic. So, yeah, I want to talk to you today about Fibonacci numbers. Um, so hopefully to some of you, this is already familiar and you know what those are. But if we were to formally define what Fibonacci numbers are, we could use a definition that uses a form of induction. So if you could, James, if you could scroll down to that little spot. Perfect. Okay. So Fibonacci numbers are these numbers that we could define according to this formula that you should be able to see on screen right now. So the 0th Fibonacci number would be a 0. The first Fibonacci number would be a 1. And then from then on, an nth Fibonacci number is an n minus 1 Fibonacci number, an n minus 2 Fibonacci number added together. So if you were to continue this sequence, it would go something like 0, 1, then 1 plus 1, 2, then 1 plus 2, that's 3, then 2 plus 3, that's 5, and so on and so on. So just to get you started, I wanted to ask if I've been told that you should be able to access pen and paper. That you should. So if you could write down quickly, I'm totally cool with you using calculators, so feel free to use calculators. But would you be able to calculate what the 17th Fibonacci number is?
It must be F17 in this sequence.
F17. Yeah.
So I suppose you've also got on there how did you calculate it, and you're not asking did you use a calculator. You're asking.
Yes, exactly. So as you're calculating this, hopefully right now, I want you to think about what is the procedure that you're following. Or in other words, in more computer science words, what's an algorithm that you're using in your head? This formula itself, the definition itself, defines a sort of algorithm that you can follow. So as you're calculating these numbers, think about the steps that you're going through. And if you were to describe them very precisely to a computer, how would you do that?
While they're talking, so there's some thinking and typing, and some numbers are going to appear on screen, I'm sure. I think maybe it's time to do the rabbit story very quickly.
Yes.
People sometimes talk about this with rabbits. There's a rabbit population model that works like this. The idea is that if you've got some rabbits, then you'll get some more rabbits. But the rabbits take a while to grow to maturity where they can have more baby rabbits. So something like the number of rabbits that you've got is related to how many you had last year, plus some new ones related to those older rabbits that you had a couple of years ago. How you actually match up the terms varies a little bit, and I've had different people do it different ways. But in some sense, the previous generations have got some effect on how many rabbits you have today, either by still being there or by giving birth to new rabbits. We could criticize this model a tiny bit. For example, the model on the screen starts with one rabbit, which is probably not enough rabbits to get things going. Good. People in chat are doing this. Yes. Oh, that's a very good one there. So Felicity says, is there a quicker way to do it rather than summing? I like that a lot. And if I were to code it, says an anonymous person, or you can be anonymous in Slido chat, that's a thing, I would use a recursive function, but as a human, I'm just calculating them in order.
Oh, perfect. This is a great segment to a section that we're going to be covering very, very soon.
Love to talk about recursion.
We will be talking about recursion. So don't you worry. Thank you for the question. Yes, but on pen and paper, you're probably just using addition and starting from 0 and going up. At least this is how I would do it. I don't know if we already got some answers.
Yeah, sorry, there's also some numbers. I haven't said them out loud, but people who've put numbers in chat have put 1,597 in chat.
Perfect. Well, if you've put in the chat 1,597, this is indeed the correct answer. So well done. I wanted to ask because one of the other answers that appeared when we showed you the initial photos was also a golden ratio.
Oh, yes. Sorry, I need to scroll, don't I?
Perfect. Yeah, no worries. I wanted to ask you, and I'm going to give you a second, so feel free to type your answers in the chat. But a golden ratio is actually quite related to Fibonacci numbers and the Fibonacci sequence as well. So the golden ratio, if A and B are two values that are in a golden ratio to each other, that would mean that the ratio of A to B is equal to the ratio of A plus B to A. So if you look at this rectangle that you can see on screen, that's blue and red, the sides of this rectangle are in the golden ratio to each other. And I was wondering if so as you can see, there is a correlation, right? Like A plus B, this is something that that would appear in the Fibonacci sequence as well. This is the same operation. So could you tell me what is the relationship between the golden ratio and the Fibonacci sequence or the Fibonacci numbers? Have a little think. There are some hints on the screen.
People in chat, I think we're already talking a tiny bit about this because there's some discussion going on.
Perfect.
Or possibly people talking to us. Lara has just said there's also a general formula though, isn't there?
There is,
so
yes.
some formula for Fibonacci numbers.
Yes, there is, and it could involve the golden ratio, so the phi. That's right. Yeah, there's a closed form solution.
Let me rewrite that from chat just to help them out. They've posted in chat that phi to the n plus phi to the n plus 1 is equal to phi to the n plus 2. Gosh. Is that true? So in one sense, this is phi to the n multiplied by 1 plus phi. 1 plus phi is the same thing as phi squared. I think that's a true fact about phi. When you square it, you get one more than itself. So yeah, I think I agree.
Yeah.
And that's the same sort of structure of adding together the previous two terms.
That is related to Fibonacci numbers. I agree. That's a good answer. Any other ideas?
I can see Joe's just told us. Oh, Aaron said it first. Sorry, Aaron. Aaron and Joe have both told us about the ratio of Fibonacci numbers.
Mm-hmm.
How do I do this? I was going to reveal it. Well, I had the fact on screen because you gave it to me. There we go. Oh, okay, so this
Perfect.
one is the phi squared thing, right? The phi squared is 1 plus phi.
Yeah, yeah. I think if you keep multiplying by like phi to the n, this is basically the same thing. So yeah, if you were to calculate the exact number of phi, which you can see in this little panel on the side that it says it under the algebraic form, you could substitute one as your b, and then a becomes phi, and then you would derive the equation that is underneath the original ratio, the one that James is hovering over. And then if you multiply both sides by phi, that leaves you with a quadratic equation. And then if you solve for the roots of this quadratic equation, then one of the roots is positive, and that is the golden ratio. So this is how you get the algebraic form of phi. Oh, perfect. James will
Sorry,
write it out for
there's the
you.
quadratic. Sorry, the phi. I've
Yes.
moved the phi on the right hand side.
Um, And then, as some people in the chat have said, what you said is exactly right. So in the limit, the ratio of two Fibonacci numbers to each other is the golden ratio.
It's quite good. So it sort of says that the rectangle you were showing me, which was made of lots of, I suppose in hindsight, those were Fibonacci numbers for the sizes of the
Yeah,
squares drawn
yes,
onto like the
exactly.
shell and the cat and stuff.
Exactly.
That they're not self-similar rectangles, but they're getting pretty close to a particular aspect ratio, which is
Exactly.
they're getting
Yeah,
closer and
and
closer to this golden ratio. Okay.
yeah.
Yes, there is a formula for Fibonacci numbers which involves this number to the power of n, which then.
Yes. That was, I think, one of the first suggestions that we got in the chat, which is also correct. Yeah, so you don't need to use the inductive definition for a Fibonacci number. You could actually derive a closed form solution, and that involves the phi as well.
I think I'm going to put the formula in chat and also, in the further reading notes, and also maybe some maths about where it comes from,
Oh,
because
great.
I think we can do that. We're not going to do it
Yeah.
live. I haven't planned it, but an interesting question might be if you start with different numbers, you get a different sequence. Can we find a formula for that one as well?
Mm. Yeah, that's a
Yeah,
good question.
and the good question is, are we ignoring the negative value of phi, the other solution to that quadratic? And the answer is no.
Yes.
People have got special feelings about the positive solution, but the other one is good too.
Yes, that's true. And I believe it's used in the closed form formula as well.
Yes.
So yeah, it's
But
definitely important too.
up to the fact that they're related to they're related to each other or something. Anyway, bro. Okay. Golden ratio aside, back to the Fibonacci numbers, back to the rabbits. I think.
Perfect. Yes. So as you were calculating the 17th Fibonacci number, I asked you to think about how are you calculating it? Like what are the steps that you are following? What are the sort of like mechanistic steps that you are following? And now we can think about, and I believe someone mentioned recursion in the comments. So we could create a very naive algorithm. So in computer science, essentially the sequence of steps that you force the computer, the poor little computer, to execute for you, we call that an algorithm. We can represent our algorithms in this form that's called a pseudocode, which is just this generic code. It doesn't really represent any programmatic language. But it gives you a sort of like recipe for what your algorithm should contain. And you'll see a lot of the same building blocks appear in the pseudocode. We don't need to really go through all of them here, but the relevant ones are, for example, an if statement. So you can see it here, and it's if a condition, a Boolean condition is met, then I want you to execute a step. That's the step underneath. If that Boolean condition, so in this case, n less than or equal to 1, does not equal true, that statement is false, then I want you to skip that step. So then you go to where the else is, and then you will do the step over there. That's one of the basic, so this is called an if-else statement. And this is one of the building blocks that you will see in a lot of different programming languages. There are also loops, which we are not using here. but we may or may not see them later. So you could have a while loop. So while a Boolean condition is true, I will keep executing my loop and evaluate at every time I execute it until the end of the loop. I will go back, check if the condition is still correct. If it still evaluates to true, then I will execute the loop again, and so on and so on. There's also a for loop, which is usually for some value that increments by some amount. I will do the set of instructions that is defined inside of the loop. But for the purpose of this super simple algorithm, we don't need to worry about the loops. This is a recursive algorithm. So what this means is recursion is very similar to induction in mathematics, which I'm sure you're familiar with. So it's quite related.
But yeah, okay. Let's say So it's about relating it to previous cases, right?
Exactly.
Is the link.
Yeah. So yes. It's not. It doesn't have to do with the proofs, but it's about relating it to the previous cases. So so in this case, the pseudocode that I'm showing you here, it defines this function that we call fib, and fib takes as an input an integer that's non-negative, n, and then it will execute the instructions that you see on the screen. And in the last step, you can see that fib calls itself. So that is what we call recursion. So fib will return fib n minus 1. So a call of the same function, but with a new input that's n minus 1 plus fib n minus 2. Do you have any questions about that?
They do. So in chat, somebody's answered. I think they're thinking about runtime already, and they've said, will it have to calculate every value up to n? And I think in principle, at least, the answer is yes.
Yeah.
Because this thing only knows, the only place where it gets to not call it itself is if you've got n equal to 0. So if you've got the sort of 0, then it can return. It can return 0. Or oh no, I see, or 1. Sorry, this is less than or equal to. I missed that. So it will return 0 for 0, and it will return 1 for 1.
Exactly.
Otherwise, it's got to do some working out involving previous numbers. It's important that it's previous numbers. If this is a plus sign here, oh no, this is now a disaster, because it's going to call higher values.
This program would in fact never finish. It would be an infinite recursive loop.
You would ask
if there was a
17th Fibonacci number, and it would try and work that out based on the 18th Fibonacci number, based on the 19th, based on the 20th.
Yes, and it would just keep increasing it. Okay. So any other questions in the chat about the pseudocode or the algorithm itself?
Yeah, I mean, there's a question about whether big O of this is related to the golden ratio, and I think we'll get there. And there's a suggestion, really, I think, here. Could you save time by saving the values? So they're already trying to improve your code. They've noticed this is not what you do when you're a human.
Perfect. Yes. So we'll get to all of this. And indeed, this is not what you do when you're a human. But for now, let's understand why this naive algorithm is a bad idea. So let's try to reason about what the runtime of this algorithm is. So some people already mentioned the big O in the comments. So often in computer science, we don't care about the exact number of, like, either the exact time or the exact number of calls or steps that the function will or an algorithm would do. We would care about the general sort of relationship of the runtime to the size of the input or the length of the input. So in this case, we have n as an input, and we'll care about what is the relationship of our runtime to n. So is it a constant time? So a constant time could mean a 10-step algorithm. It could mean a 100-step algorithm. The important thing is that that constant is unrelated to n. So it's a fixed number of steps. So that would be, and that would correspond to this notation of big O that some people mention of one. That means constant time. It could be a logarithmic time. So it means that it scales logarithmically with the size of n. It could be a linear time. So it could be O of n. It could be a quadratic time. So it could be O of n squared. Or it could be factorial or exponential. Those are the bad cases that we usually would want to avoid. So I want you to think about the number of steps that this program would take, but in these more general terms. So what is the relationship of the runtime to the size of n? And in order to help you analyze that, I wrote two versions of this little pseudocode in Python. So the first one, the one at the top, is basically the exact same thing that you've seen in the pseudocode, just implemented in Python. And then the second one should help you think about how many steps this program actually executes. So every time we do a constant amount of work, so where I've put the print statements, this is like one step. And we could think about how many steps where this program prints a statement, how many steps is it going to take? So have a little think. This is a recursive program, so it is a little bit tricky to wrap your head around how exactly it works because so a good thing to think about this is step through the program step by step. Pretend you're a computer and pretend you're just trying to understand the instructions that are written for you in code. So step through it step by step and try to see what happens. And try to, if you can, try to give me a relationship of the runtime to n. So how do you think it'll scale with n?
I see. Okay. This has got a kind of implicit else going on, right? That if something's not indented for the ifs, then
Yes.
yeah, no,
Yes.
I'm
So
getting there.
Python uses indentation. So it
Yeah,
means
and
that
also if it
a block.
returns, then it doesn't do the rest of the lines. So
Yes.
I'm thinking about
Yes.
fib2 to just try and work out the second
Yes.
Fibonacci number, and the key
Yes.
is that this if is not satisfied, so I ignore this indented bit. This if is not satisfied, so I ignore this indented bit, and now I get to do some printing. You need to calculate
Exactly.
f1. You need to calculate f0.
Yes.
Right, and it will call the function. So I also need to go and think about f1 and
Exactly.
f0.
So in fact, you
Both
wouldn't
the previous
step
ones.
into, you wouldn't step into the other print
I
statement.
don't even get. I don't
You
even get
would
down here.
execute, you would
I need to do
execute the
fib
recursive
one.
call first.
I
Yes, exactly.
see. And fib one is a bit of a special case, but I see in general,
Yes.
in general for a large n, you don't do these top bits. You get down to that first print statement. You think, oh, I need to print some stuff. You start calculating the first one, and that
Yeah.
might do some shouting as well. I've described your code as noisy because it's going to do lots of shouting during
Yes.
during this.
Yes.
People in the chat might be guess. Yeah. If you've not done coding before, where am I going to point the camera? I'm going to point the camera up a little bit because all that the stuff below is doing is trying to.
It's the same.
Yeah, it's the
Yes,
same as
it's the
this thing at the
same
top.
as the pseudocode. So yeah, especially the bottom one, really don't worry about it. Try to think about like how many steps will the program take.
How many times? I suppose it's also how many times does it call the Fibonacci
Yeah,
program
that's
itself?
also another, yes, yes,
Right.
yes. That would be a great way to think about it.
It
Like
looks
how
like
many times, because if you're not doing recursion, I think I have a little note about this somewhere below. If you're not doing a recursive call, then this program takes a constant amount of time. So this is an O of one time when the recursive step is not being executed. So then this means that to calculate the actual runtime, all you need to do is figure out how many times do I need to call the fib function itself? Because every single call at a leaf, at like the base case, is constant time.
You can kind of get a feel for this, I think, if it's this question about how long does it take, roughly speaking, is something like Ola's been nice to you by saying calculate F17 earlier. If that is instead F34 that Ola asks you for, and you've got okay, roll up your sleeves, ready. How long is that going to take you, roughly speaking? About twice as long, maybe? Is it linear? Is it proportional? Or maybe it's 4 times as long because these things are sort of quadratic. Or maybe it's just sort of infinitely much worse. I think for people going at home, somebody said it should be ON, order N, or kind of linear. I think for people doing it at home on paper, that's the right answer, isn't it?
For people doing it at home on paper, this is the right answer. And this is the counterintuitive thing about recursion. And the reason why implementing it this way is potentially maybe a bad idea.
Yeah.
And we can show you with James together what happens when you actually execute this program. So I've just executed it for n equal 5. So
Okay.
I've run the code that I've written with the extra print statements. So think about any print statement as like a constant, constant amount of runtime. But you can see how many print statements we are getting. So every time the program hits the recursive step, it's like, okay, you're asking me about fib of 5. I need to go and calculate fib of 4. And then it tries to calculate fib of 4, and it's like, well, okay, I need to calculate fib of 3. And then it needs to calculate fib of 3, and then it goes down to the line where it's the recursive step again, and it goes and it's like, oh, okay, I need to calculate fib of 2. And then finally, when it's trying to calculate fib of 2, now it's like, okay, I need to calculate fib of 1. I know how to do that. And then fib of 1
Okay.
is ready because it's the base case.
It's
So
kind of
you've
what one.
hit the base case. Yes.
I
And
see.
now, and now you still need to calculate fib of 0. And then fib of 0, you also know how to calculate. And once you have fib of 1 and fib of 0, you can now also calculate fib of 2. So if you look at it sort of like more broad, like this is, if you go from fib of 5 and see it and try to understand what happens, I tried to draw these brace brackets for
Oh,
you.
right, yeah, yeah.
So in this first chunk that I highlight in the first bracket, this is how many steps we need to calculate fib of 4. And then in the next bracket, I'm showing you how many steps we need to calculate fib of 3. So these are the two recursive calls that we make initially at the top level when we're trying to calculate fib of 5. And then at the very bottom, this is just a constant amount of time at the very end. When I have fib of 4 and fib of 3, I just need to combine them to get fib of 5, add them together. So these are the three chunks. And then if you go inside of the fib of 4, this is the next set of brackets, so 1 over. Now, inside of the calculation of fib of 4, I need to calculate fib of 3 and calculate fib of 2, and then combine them together. And then if we were to, yes,
I'm almost
exactly.
just that box. Is it working out F3, which
Yes.
is the number 2? So this is the number of calls it's doing, or the amount of backtracking it's doing to work out
Yep.
that 1 plus 1 is 2.
Yes.
Welcome to the
And then
Oxford.
inside of that, it needs to do
It's got to go and look. It's
fib
got to
of
go and
2.
look those things up, right? Not only
Yeah.
has it not remembered F16, and it could just piggyback on F16 and F15. It doesn't come with any
Yeah.
of the previous ones loaded. It doesn't even remember them during the calls.
Yeah,
That they
no,
all
it
happen
doesn't. It has
separately.
no memory. It's like the silliest program you can imagine. Whenever you ask it, so you can see how many recalculating of the same thing it's doing. Like it's, for example, it had to already calculate fib of 3 um, before in this on this like second level, right?
Yes, down
So
here.
when it's
Oh,
Yeah, this
sorry.
is like the most top down, but like
Oh,
even
this
when
is
it
what.
was
Yeah.
so at first it would do the whole recursive call of fib of 4. And inside of the fib of 4, it already calculated fib of 3. So then when it's doing the bottom call of when it's calculating fib of 5, when it's trying to do fib of 4 plus fib of 3, all of the calculation for fib of 3, it's already done. So maybe I should be able to also
Oh,
point,
yes, wait.
right?
Yeah, yeah, yeah.
Ah, yes. So here, this is doing the
Sorry.
calculation for fib of 4. Yeah, you can see my
I can
mouse
see. I
with a
can see
little bit of lag.
it.
Yes. And inside of this call to calculate fib of 4, it already here in this bracket, it calculated fib of 3. So then when it's finished with this whole recursive call to fib of 4, and now it just needs to do the other part of calculating F5, which is add fib3. It should remember all of this. But I didn't draw the brackets for this anymore. But to calculate the fib of 3, it would do another tree over here.
Oh, it'd be
So
all of this,
it
wouldn't
would,
it?
yeah, yeah, it would do all of this again. So
Oh, sorry.
no,
I
no
thought I could
worries.
just copy paste it. Sorry. Wait, I
No, no
can't see
worries.
with most of my computer. My computer is doing order some amount of computation to get everything in the right place. There you go. All of that, right?
Yeah, yeah,
And also
yeah,
all of this
exactly.
there. Yeah. So this is a lovely tree. Like it goes very deep and then it comes back again.
Yeah,
And then it goes very deep
yeah,
the second time. That's kind of the pattern. But within that it's going deep and less deep.
yeah.
Yes, I think we lost some frame rate on that operation. This little maneuvers are going to cost us cost us years. Zaid in chat asks
Oh,
about return because that was the thing in the computer code. Return just means print and give the number out. In the old days, it
yeah,
would literally print it on a bit of paper. These days, it
yes.
means it
So
gives it as an output of your function.
exactly, yeah. So we use functions a lot in computer science, and a function can have an input, although it doesn't have to. So in our case, our fib function takes n as an input, and then this return block that you're asking about, this is exactly like James said. This is essentially return something is usually the syntax, and that something, whatever follows the return, is going to be the output of the function. Um,
Nice. Okay, so this code that uses recursion, which is a nice computer science concept in general, uses recursion but has turned out to be extremely silly as a program.
yes, exactly.
It sort
It's
of
a very
explodes
silly
into lots
program.
of calculations.
Yes. So this is, I think it's best probably, I think it would be very hard to calculate also because of how I implemented these print statements. But maybe you could give me some wild guesses based on like how you can sort of see the program scale. So you can see that that it has a lot of redundancies, that it does a lot of stuff many, many times over, even though it's done it before. Have a guess. If the program was given the same instruction that you were given at the beginning of this session to calculate the 17th Fibonacci number, so in our new notation, this is fib 17, um, how many lines do you think it would print?
Right. Because we've seen that
So
it.
I've shown you the lines for fib 5. Um, that was like 20 something probably lines. Um, how many lines do you think it would print if it was fib 17?
Nice. So, Ruben in chat said something a while ago about how does the complexity here, or the amount of stuff you're doing, has the same structure as the Fibonacci numbers. So possibly the complexity scales with the sum of the complexities of the previous two, which would mean it does the same relationship as the Fibonacci numbers.
That's sort of true. Yeah, you can see
But we've
that in
also
the
got so
in
we've
the
got
tree.
yeah we've got
Hmm.
a guess of then 1597 lines. course, F5 takes more than 5 lines because there's lots of different sorts of lines that we see, lots of different print statements on the way.
Yeah,
But I guess I'd expect it. I don't know. So there's
it
a
might be a little bit bigger than what you're guessing
factorial
right
or
now.
exponential. It is exponential, isn't it? It goes exponentially fast. And there's a prediction of 2 to the n with a question mark. I can see
Oh,
where 2 to
good
the n comes from,
prediction.
right? Because
Well, yeah, yeah. Two to the end is a great prediction. So this is a great back of an envelope sort of answer. Yeah, really good. So if you want the exact number, because I've checked that before this session earlier today, the number of lines, this particular lines that I'm printing here, um, the number of lines for FIB 17 is 10,331. So our scaling is not so amazing. Our program becomes exponentially slower as n goes up. So it will be, we will be doing the runtime relationship to n will be exponential.
yeah, so there's quite a lot.
It's quite a lot. Usually we
There's
want
some,
to
yeah.
usually we want to avoid exponential runtimes at all cost. But this is a very naive, very primitive implementation that you might want to start with and optimize further. So if you're curious about where the exponential comes from, James, if you could scroll down a little bit.
Ooh, yeah. I've scrolled down way too far. Somewhere in here. There we go. I found it.
Yes, that's
Also, in
perfect.
time that it takes to run.
Yes, so if we can, so this tree that I'm showing you here, so T, we can think of, like we said before, we can think of the number of times that we need to call the function fib. And if it's, if you're calling the function with either 0 or 1, you will just return in the first call. So there's only one call to the function that you need to make. However, if n is bigger than 1, then you will need to do the actual recursive call. And this is shown to you by this formula in the second line. And you can see how this creates this tree structure where you see the yellow nodes. And this is very similar to what we saw in the lines that I was printing, where we had these curly brackets. You can see how this tree structure appears. So hopefully this makes a little bit more sense. And then if you think about how many levels are in my tree? So this tree is a little bit special. If you want an extra take-home exercise, you could try to work out exactly the number of nodes in this tree, because the left subtree and the right subtree are not going to be of equal depth, because one subtree is tn minus 1 and the other subtree is tn minus 2. So there will be a depth difference of 1 between them. But let's ignore that for now. Let's just look for what we call an upper bound. So if we're going from tn to tn minus 1 to tn minus 2 and so on and so on, at the bottom eventually we'll have t1. So we would have had, at least on one side, n levels. The depth of the tree would be n. And then let's think about how many leaf nodes, so the bottom nodes we have in the tree. By the way, in computer science, we love trees. We use them in a lot of algorithms. It's a very useful structure to have in mind when you're designing some of the efficient search algorithms and stuff like that. So if you are interested in computer science, you will see this tree type of structure appear a lot in all sorts of different places. It's very useful. But yeah, back to our tree. If you think about, so look at this tree that we have drawn here. We go from tn to then tn minus 3. So if we go 3 levels deep, then we have 2 to the 3 leaves at the bottom, right? Do you see it? At the bottom, we have 2 to the 3. So following this logic, if we had n levels, right, we would eventually have 2 to the n minus 1, sort of. So here we have 4, if you count the root, we have that 4. At the bottom, we have 2 to the 3. If we had n, we would have 2 to the n minus 1. So the total number of the nodes in the tree would be close to 2 to the n, which is one of the answers that someone suggested in the chat. So it's a very good upper bound for our algorithm, and it shows you that it will be scaling exponentially. And in fact, for the exact code that I've shown you above, I've run this code for different inputs, which is what you see on the x-axis. So the x-axis shows you different values of n, and then the y-axis shows you the time in seconds that it takes to run this program. And you can see an exponential curve appear. So, and my, the server that I was using to run this was definitely struggling when I was trying to run these larger numbers. You can see how this is a trend like that we would try to avoid at all costs, because then if we had to calculate larger Fibonacci numbers, this would be really, really bad for us, and we would need to wait for a very long time. So there were already some suggestions on how to do this better. And probably when you are doing this on paper, you are not running into the same recursive issue. So what is the main problem of this algorithm? What would you try to fix to make this more efficient?
What would you fix? What would you do differently? A couple of points from chat. I've been keeping an eye on chat as well. Someone asked, is this part Tn minus 1? Is this twice the size of Tn minus 2? And it's not quite twice the size of Tn minus 2 because it contains underneath it a copy of Tn minus 2 and Tn minus 3, which is something slightly smaller, plus this node itself. So it's kind of, its rule is that you sum the previous 2 plus 1 for adding them together at the top, joining them together at the top. So it's slightly asymmetric. So far at the top, we're imagining that n is a large number and it's splitting out like 2 to the n. But then some of these do eventually get evaluated as 0 or 1s. We saw it in the braces that you had, where it wasn't 2 symmetric copies. It was
one was smaller than the other.
One was smaller than the other. It was a subset of the other.
If you want to have it as a little take-home puzzle, you might be surprised as to what number will appear in your solution, and you may or may not have seen it earlier in the session today. But yeah, I won't spoil it any further. I think it's a fun exercise to do. Any suggestions for how we can improve this
Chat
program?
would really like it if we could. We're calculating the same number of loads, so we should save them. Felicity says,
exactly.
Save solutions.
Exactly. We want to save the solutions to subproblems. So we have a name for this in computer science. It's called dynamic programming. Very fancy name to say a very simple thing, which is we want to remember or store solutions to subproblems. That essentially is what dynamic programming does. So here I want to introduce you to a slightly new concept that we also use in computer science a lot, and this is a concept of an array. So array is just a fancy way of saying I'm going to store, instead of storing just one thing in one variable, I'm going to have this slightly more complicated variable that we're going to call an array. An array can store n things, and I can predetermine n in some languages. Array allows me to store n things, and we can use an array here to store the numbers that we've calculated before. So this will probably be very similar to a solution that you've implemented on paper when you were calculating the 17th Fibonacci number. So maybe it's helpful if we go through this code together. So the beginning of this code is very similar. We take our input, which is n. We go, we check if n is less than or equal to 1. So this is our if-else block. So if n is less than or equal to 1, if this is true, then we can just return n. So this means output n, you're done. Finish the program. If it's not, so this is now we are in the else bit, then we enter the block in the else component.
So we're now
sorry if I'm going too quickly.
No. I have to write really slowly because my handwriting is bad. Else, so you've got this arrow. Oh, is this a label? No, what is
this? This is an array. So this is this new concept. So array, you can think of it as just a long box with n slots in it, and you can put things into these n slots. So yes, exactly. Yeah, perfect.
I should probably leave larger gaps, shouldn't I? But yep, here we go. Okay. So set up an array, which for your computer language means something like, "Oh, go find some memory, allocate
exactly."
memory.
Yeah. Yes, exactly. And then we're going to. So now we have an empty thing, like James just drew, of size n. So there's n of these squares, and then all we're telling the program in the next line is, oh, in computer science we always start counting from 0. So the first box, 0th box, in the 0th box we'll put 1.
Maybe 0 for the 0th value.
According to our definition, it should be 0. So we can put 0. Let's pretend the program says 0.
Okay.
Yeah.
And then
let's say 0.
Okay. And in A1, so these square brackets mean go find me the square box.
Exactly. Number, so basically. The square brackets mean in the location 1, put the thing that I'm assigning to this. So put 1 in there. And then we have a loop. So now we're going to iterate over this value e, and we're going to, in each iteration of this loop, e will increase by 1. So I will start at the value of 2, and then it will go up until n. And when it hits n, the loop will finish. So in the first iteration of this loop, I is 2. And then we're telling, the instruction is that for the array in the spot 2, we're going to put whatever is in the array at the spot 1 plus whatever is at the array at the spot 0. Or the other way around, actually, the way it's implemented.
I look at those, I see they're 0 and 1, I'm told to add them together, and that gives me the number 1, which I put in later. And I see this is exactly what we were doing on paper, isn't it? This is how you would do it on paper.
Exactly.
You look at the previous 2, you have them written down in an array or on paper, and you always look at the previous 2. So this is an implementation where you're looking back at the previous ones.
Exactly.
To n.
Exactly. And then the loop will go back up, but now I will be incremented by 1. So in the next iteration of this loop, I is 3. Mm-hmm. And then we're telling the instruction inside of the loop is now in the box 3 of the array, sum up whatever is in the box 1 and in the box 2. So in this case, this would be 1 plus 1. And then in the box 3, we would put 2.
Oh, yeah. So I need to sort of increment all these values because I is now a larger number. This is a terrible way to do it. I should have used an eraser. Okay, right. And then add them together and I get the next value. 1 plus 1 is 2. Welcome to the Oxford Online Math Club. Good. And then keep going, which is, that's what you do. You look at the previous 2.
Yeah. And this is probably quite similar to what you did on paper, just with this fancy notion of an array, which is this long box of values. Do you have any questions about that?
Well, they have already asked whether people have tried to start deriving the formula from before, so I'm getting distracted by that. Ruben said, "Is this now order order n, because I guess earlier we said that if you did it on pen and paper, it's order n because you just look for each one
Yeah.
up to the one you want. You do that. That's what this code's doing.
Mhm.
I hope it's order
Yes.
n. It's
So
order n.
this it is order n. Yeah, that this is a perfect answer or a perfect question if this was formulated as a question. It is because now we've gotten rid of the recursion, as you can see. There is no more recursion. We just have this array, which is just like this fancy box in which we can store things. And for every iteration of the for loop, we will just do a constant amount of work. So it'll take us a constant amount of time to do a little bit of work for every iteration. And we have n iterations. So we're going to do n times a constant amount of work, which gives an order of n. So this is a linear program. And you can see here, this is the actual code that I've written. It jiggles a little bit because I run it. There's this thing that some of you, if you've played around with coding, maybe you know that there's this website that's called Google Colab, where you can use some of the Google servers to run your code on. So that means you don't need to install Python. It's in the browser, and you can just run your Python code. But because it's running on a server, it also means that sometimes you're sharing resources with other people. So the line might be slightly more jittery than if you were running this on the computer. And now if you look at the y-axis, so it's the same graph as before, but you can see a linear relationship between the x and the y-axis, give or take the jiggles. But the reason also you're seeing the jiggles is now the scale on the y-axis is no longer seconds, is seconds. It's a second times 10 to the minus 6. Yeah. So it's
I missed that.
significantly
It's
faster.
not in actual
Yes.
seconds. Google Colab
Yeah.
would be very cross with us if we implied that it took
Exactly.
an entire
Yeah, so
second
it's
to add together two small numbers.
exactly. It's really fast. So in comparison, if you look at the plot below,
Oh, I was going to do
if
louder.
we compare the runtime of our recursive implementation, which is still in blue, to our now new fancy dynamic programming implementation, which is in red in this graph at the bottom, you can see how much faster the new one is. And now we're not getting the same, scaling relationship. The scaling relationship is linear. Linear is usually pretty good, depending on the problem. But yeah, like we're much happier with linear than we are with exponential for sure.
Nice.
We're low on time, so I will just hint towards a little extra bonus question that you can answer in your free time later, which is to do with our use of memory this time. So far we've been talking about time, but now that we've introduced this array, we are also using a linear memory because we're storing n things. So a bonus question is, do we actually need to store all n things? Or could you also optimize the memory? But that's something that you can think about at home.
Can you do this without? It'd be good. I guess for people at home, that would be, can you do this using less paper? But I suppose computer memory is not quite the same as paper because
Yes,
you
it's
can.
could you think about if you were doing this on paper, would you have to see all of your previous results? Or
Yeah.
could you completely forget some of your previous calculations?
Anonymous says someone was talking about this, and yeah, can we just somehow store the previous two? Just store the previous two
Yeah,
somehow. So maybe a
yeah,
very short
that's
array that we
yes,
constantly
yes,
pencil and
yes.
paper.
And that
Pencil and paper. I can do
ex
it with a small bit of paper.
exactly, yeah, if you just have a very, very tiny amount of paper. Exactly, yeah. So you could just store two things. And that's enough. And then in this case, this is also constant memory. So we were talking about constant time before. Our program is linear in time. but it was also linear in memory. But if you're just storing two things in memory, two, um, then you would also have constant memory, which is better than linear, obviously.
Good. I'm going to zoom back to all of this at once. Yeah, let's zoom. Let's do a big zoom out for the end of the episode. There
Yes. So
we go. Get the
if
cat.
we're
Get the
just
cat in.
going to
Okay.
summarize really quickly the stuff that we've talked about, and if we were to think about some takeaways for you, what I would like you to leave with is that, first of all, like computer science and maths share a lot of the same things. There's a lot of mathematical and logical thinking involved in computer science. So there's a high chance that if you like one, you will like the other. The second thing is that in computer science, we care a lot about this computational complexity or the runtime. And we care a lot about optimizing things to be faster. Because if you don't care about it, then you could end up with implementations like our original implementation um, with recursion to this Fibonacci sequence, which, by the way, I don't want to paint a picture that recursion is a bad thing. Sometimes it's extremely useful and you can do things very efficiently with recursion. Um, but in this case, the way we've used it is not is not optimal in any way. So this is a way that we would try to avoid. But generally speaking, oftentimes, if you implement solutions naively, then you might end up with these factorial or exponential runtimes, which are really quite bad. And there's often better ways of doing things. So that's another takeaway. And then finally, if you were confused about any of the code because you've never seen any coding before, don't feel discouraged. This is something that you could learn very quickly. There's just a few building blocks that we use in coding. And if this was my focus during this session was not to really introduce you to these blocks. So if you found any of the coding or any of the specific steps counting confusing, don't worry about it. You would get it very quickly if you spend a little bit of time with it. So it was more a lesson on like how we care about complexity and how we care about like how long our things take to run.
Yeah, sometimes mathematicians worry about writing proofs up and being able to write down mathematics is important, but also having the ideas or understanding what the ideas are is a sort of separate
Yeah,
important idea. Which I love that that's part of computer science, of course, because
yeah,
selecting the right algorithm or the right way that your algorithm works can save you more time than just using a bigger computer or something, or waiting for the next generation of computer. You could, while you're waiting for them to invent a bigger computer, you could have a better idea about how your code works. That means that actually you
exactly.
just run straight away on an old laptop rather than waiting for a
Exactly.
faster machine. That feels like a lot of math and computer science at the moment. We've done a lot of we did some RSA cryptography a while ago, which sort of feels like you can wait for some hardware to come along that might solve this hard problem. Or maybe you could just have an idea and
Yeah,
bam, don't have to wait for it at all. Right. Okay, thank you so much Oya, for coming on and telling us about Fibonacci numbers and the golden ratio and complexity.
of
Uh,
course.
it's
Thank you for having me.
that's okay. It's the end of our episode, and we're having a couple of weeks off for the Easter holidays. So we're going to be back, same channel, same time of the week. Because of the break, that's going to be, sounds a lot, 503 hours, I think, for two and a bit. We always say how many hours it is till the next episode, so they know like how long to wait until more Maths Club. Before then, we've got lots of past episodes. I really think it might be 100 now. I should have counted. On other topics and further reading notes. If you go there, we'll post further reading notes for this episode tomorrow. But after that, we'll be back in 3 weeks' time for another episode of the Oxford Online Maths Club. So goodbye from both of us, and I'll see some of you in 503 hours. Take care. Bye.
Bye bye.
To be clear, that's a lie. I've left it saying back next Thursday. Hang on. Back soon. There we go, fixed it.